our next speaker, Sebastian Pokutta. It is my pleasure to introduce him as the second keynote speaker of MIP 2020. So Sebastian is a professor of mathematical optimization at TU Berlin, and he's also the vice president of SUSE Institute Berlin, which is where I'm currently physically sitting. And that means that the two of us work on the same office floor. Well, 2 months ago when working in an office was still a thing. Haven't actually seen each other for quite some time now. So before joining ZIP and TU Berlin, Sebastian was a professor at Georgia Tech and the University of Erlangen-Nuremberg. He was also a postdoc researcher at MIT and at IBM iLog after he had received his PhD from the University of Duisburg-Essen in 2005. So you might recognize a pattern here of moving back and forth between Germany and the US, back in the time when traveling was still a thing. And Sebastian's research is situated at the intersection of artificial intelligence and optimization. Furthermore, he loves the theory of extended formulations and exploring the limits of computations in alternative models of complexity. Applications that he has worked on include the coordination of autonomous vehicle fleets, clearing of electricity markets, cyber-physical systems, and predictive pregnancy diagnostics. Really interesting stuff, and many more. Sebastian up to now has published more than 90 research articles, and his work has won numerous awards. And today he is going to talk about his latest research on what comes beyond worst case rates. So I'm curious to learn about this. MIP is on, and now Sebastian is on.
Thank you very much for the very kind introductions and for the organizers to invite me here. And I would also like to thank and wish Dan a very happy birthday. Let me see if I can share my screen 1 second. Can you guys see my slides?
Yeah, perfect.
All right. Yeah, thanks a lot. So what I would like to talk about today is a data-dependent rates in learning and optimization. And the context here is something that we are all very much aware of, which is that we often derive some type of worst case guarantee by means of a convergence rate or an approximation guarantee. However, then if you look at specific instances, the performance is usually much better than what these guarantees predict. And what this talk is going to be about today, 1 second. Guys, can you see my slides?
Yes.
Okay. So what this talk is going to be about today is finite data-dependent complexity bounds. And the focus here today will be really on optimization and not so much on learning, although of course you very naturally get from optimization to machine learning because you have these types of ERM problems that are usually solved by some form of optimization algorithm.
Could you enter like a full screen mode?
Yeah, I was in full screen mode. Let me see what's going on here. I had this earlier today. Give me 1 second. Let me try something. Let's see if this works. Is it better now?
Yes.
Perfect.
Now we see it in full screen.
Sorry about this. Technical complications in the new format. All right. Good. So outline of the talk today will be as follows. I will start with a very simple example, which is from the context of convex optimization, where these data-dependent guarantees really come from. And then I would like to look at 2 specific examples. So the first example is from submodular function maximization. And the second one is from, let's call it convex geometry, and in fact deals with the approximate Caros-Theodore problem. Just a note, I'm pretty sure that my references are not exhaustive here, and I apologize in advance if I forget to cite important work, and please also check the references contained in those that I'm citing here. All right, so let's get started. So our starting point is the following simple problem. So we consider, what we want to do is we want to minimize the convex function f. And this convex function is of the form 1/2 a minus x ax minus b 2 norm squared, and that is just a simple linear regression problem where a and b is data. So if you look at that function, it's not so hard to see that this function is convex and smooth. And one way of doing this, very standard way, would be to use, for example, gradient descent, which would mean that you would build or form your new iterates xt plus 1 as taking the previous iterate xt minus 1 over L gradient of f of xt, and the L is here the Literalist concept of the function. So yeah, so suppose we do this now. So what can you expect? So since the function is smooth, we can invoke the standard guarantees that we get in convex optimization, and they would basically predict that the primal gap here, this f of xt minus f of x star, is basically contracting at a rate of 1 over t, and the initial distance is, or the initial value is basically the Lipschitzness times the initial distance squared. So that's an okay rate. That's not a great rate, a convergence rate of 1 over t. And let's say you are interested in doing better. Let's say what you would really like to have is something like a linear rate. So what this usually requires is some form of strong convexity, for example. And what linear really means here is that this primal gap that you have contracts with a linear factor, say a factor 1 minus alpha. So in every round, you close the residual gap by a multiplicative factor. And that's what people in convex optimization refer to as a linear rate. And usually you can get this, for example, if you have strong convexity. So let's say we'd like to do this. And what we very soon realize is that our function f is actually not strongly convex if the system ax equal to b is underdetermined, which is nothing else than saying that A transpose A is not PD. So it seems like, you know, you have to fall back to the worst case rate of 1 over t here. However, if you implement this, this algorithm here, so basically using gradient descent to solve the problem, you will effectively always observe a linear rate. So there's a big discrepancy between the 1 over t worst case rate that you get from the standard analysis and the rates that we actually observe in practice. And to understand this a bit better, let's go back to basics here. And what our starting point is basically the following. So let's suppose we look at this function and we have this f of xt minus f of xt plus 1. This is just really the primal progress that you do in iteration t. Then by standard convex optimization theory, and I will not go into any details here, you can lower bound this progress as basically 1 over 2 times the Lipschitzness times the norm of the gradient squared here. So this is a standard bound in convex optimization, very often referred to as the progress lemma. So that's basically a very simple fact. What's not quite as simple is the following thing that you can prove, which is due to Garber and Hassan in 2015, as far as I know. And what this basically shows is that the norm of the gradient squared here can be also lower bounded by the minimum eigenvalue of AA transpose times the primal gap that you have from iteration t. And what's important to note is that this AA transpose here is actually now a PD matrix, and the minimum eigenvalue is as such bounded away from 0. And if I now chain these two inequalities together, so I put this inequality in up here, what I actually obtain is that now my primal gap is again contracting at a linear factor. Namely, I have this factor here 1 minus the minimum eigenvalue of AA transpose divided by 2L times the primal gap of the previous round. The key point here now is that this convergence rate now directly depends on the data of my problem, namely in this case, the matrix A. And yeah, so that's just like an introductory example here. And in that context, we typically care for 3 types of questions or inquiries. So the first one is that you would like to establish the existence of some data-dependent guarantee. Why do you want that? Because it basically says that your algorithm is a good algorithm because it reacts well or adapts well to data in some sense. And what this means in our example, for example, is that you have this data dependency here due to the smallest eigenvalue. Now something important happens. So just obtaining these rates or these guarantees is a nice thing, but it's typically not good enough. What you really need then is that you need to find an algorithm that is adaptive to those rates. And what I mean by this is that you do not need to put any a priori knowledge of this data, in this case here, the minimum eigenvalue, into your algorithm. And now if you go back to what algorithm we used here, which was gradient descent, then you see that our updates did not depend on A, just on the Lipschitzness here. And this is why the Lipschitzness itself is part of the input versus the data dependency here is not. So in order to leverage these guarantees, what you typically would like to have is an algorithm that automatically adapts to the sometimes benign properties of your data and then potentially performs better. And the third thing that people typically care about then is whether you can improve the performance through data preprocessing. Once I have established such a data dependency, such as up here, if I now preprocess my data to maybe improve the minimum eigenvalue, this will immediately improve my convergence rate. But that's something that is a bit out of scope for today, so I will not have time to talk about this. So yeah, so what I would like to do now is I'd like to basically try to carry over this concept to two applications. So the first one is joint work with Mohit Singh and Alfredo Torrico. And the context or the topic here is submodular function maximization with a single cardinality constraint. Just to recall some basics here. So we have this function f, which is monotone submodular. Just for notation and recalling things. So we have the marginals here, which is basically the increase in function value that you observe relative to a given set A when you add element E. Then you want the function to be monotone, which basically means it respects subset relations. And you would like to have submodularity. Submodularity means that you have decreasing marginal gains. So if I have a larger set that contains a smaller set, then the gain with respect to the smaller set is better, or at least as good as the gain with respect to the larger set. So that's just to recall some basics here. The problem that we are interested in is we want to maximize that submodular function f, subject to the constraint that we can pick up at most k elements. And yeah, so what is known about this? So what is known is that there's, for example, the greedy algorithm. And what the greedy algorithm does is it basically proceeds in k steps. And in each of the steps, so it starts with the empty set up here, and in each of the steps, you add the element with the best marginal gain that you have not already picked up in your set. And that you do for k steps, and then you stop. And then what you can prove is that the greedy algorithm provides you with a 1 minus 1 over E guarantee here with respect to the optimal value that you could obtain. Now, however, in several applications where we are actually able to compute the optimal solutions, it turns out that the greedy algorithm performs much better than what this worst case guarantee predicts here. And what I would like to try to do now is I'd like to try to give a or another explanation why this might be the case. So yeah, for this, we will make a very short detour to convex optimization. And I apologize for the references to convex optimization all the time, but it's really that from that context, all these data dependent guarantees stem in one way or another. So we start out with this smooth and convex function. It really doesn't matter that much what this means. I assume convexity is pretty clear, and smoothness just means that the gradients are not too crazy and not suddenly changing for our purposes here today. And then there's a very important context in convex optimization, which is referred to as sharpness. And what sharpness basically does is it tells you how fast the function curves away, so how fast the function value is increasing with relative to the optimal value when you move away from the optimal solution. So think of the y as being my optimal solution. It's just that you potentially can have more than one optimal solution if the function is not strongly convex. And on the right, you see a couple of illustrations what this sharpness really means for the curvature of the function around the optimal solution. And the reason why you care for this is because this sharpness condition with convexity immediately implies the inequality that you see down here, which basically states that you get some lower bound as a function of the gap here between function value gap between x and x star, and this lower bounds the value of the gradient at position x. And so this concept of sharpness is a very well-known concept. It's known under many different names. One is Hölder error bound. Another one is the Polyak-Lojasevic condition. And so once you have this inequality here, what you can do is you can chain it into the smoothness inequality that we have seen earlier. And what you then get is basically a similar contraction to what you have seen beforehand. So you get that the primal gap in iteration t+1 is basically some factor, we talk about the factor in a second, times the primal gap from the previous iteration. Now this factor is a bit different than what we have seen beforehand because it depends on the primal gap itself. And it also depends on these parameters c and phi here. And usually what you get is you get a smooth interpolation between the 1/t worst case rate and the linear rate here. As I said, this has been known for a very, very long time. I mean, that's not, this type of bounds are not new. What is new, however, is a way of actually leveraging these bounds in algorithms by making algorithms adaptive. And that's only due to Roulet and Daspoumont in 2017, that we know how we can use certain restart schemes that allow you to have an algorithm, an optimal method, basically, tap into this extra potential from sharpness without having explicit knowledge of the C and the phi here. So what we want to do now is we basically want to derive a similar type of concept for submodular functions. And let's start out with the most basic one, which also turns to be out in computation the most useless one, but I'll talk a bit about that later. So let's again pick a submodular function f that is monotone. And if there exists an optimal solution as star, such that the following inequality holds, we say that the function is C phi sharp. So what does this inequality say here? So rather than parsing it as it is, I would say divide by the cardinality here to the 1/phi power. And then what you basically get is something like a certain norm of the average marginals here, which are the equivalent of the gradient in the context of submodular functions on the left-hand side, and on the right-hand side, you basically get something like the primal gap because the function is monotone here. So you get a mechanic that is very similar to the sharpness condition that we have seen earlier. And just for completeness, this is really the most basic version that you can come up with. We have much better version, so-called submodular sharpness and dynamic variance. And the performance, as we will see later in computations, is also much better. And I also need to mention that there are other concepts that do something similar in terms of giving better guarantees. So there's, for example, the notion of curvature and stability that also do improve with respect to the worst case guarantees, but they are somewhat different in nature, as we will see a little later. All right, so that's about that. So what you obtain if you use this monotonic notion of sharpness here for submodular functions and also all the other notions that we have is that the greedy method, the greedy algorithm, automatically adapts to these notions of sharpness. So in the case of monotonic sharpness, what you obtain is that the set that the greedy algorithm produces has a function value that is at least 1 minus phi over c to the 1/c times the optimal value. And rather than parsing this value here, just note that what this really does is it interpolates between 1 minus 1/e and the best case. And before I give you a proof sketch now, I just would like to mention one thing, right? The very natural question that you might ask now is like, well, that's all nice. You have this notion of sharpness, but maybe there are no functions that satisfy this notion. In fact, quite the opposite is true. So there's something like the Lojacevic factorization lemma that, for example, in convex optimization ensures that basically basically all sub-analytic functions satisfy the sharpness inequality for non-trivial constants in a compact environment around the optimal solution. And similarly here for submodular functions, you can similarly show that these functions satisfy this notion of sharpness with non-trivial constants here. All right, so now let me give you a very brief proof sketch how this works. So so what you see here on the left-hand side is again the primal improvement. So the proof always basically follow the same template. So on the one, you start out with the primal improvement here in iteration I in this case. And this is lower bounded by the average marginals of those elements that you have not picked up yet. And this inequality is just the greediness of the algorithm that you're using here. And now what we do is we take this inequality and we chain in this monotone sharpness inequality for the cardinality term down here. And what happens then is that you get this chain of inequalities. Just trust me that I did my insertion exercise here the right way. And what you get then is you get this vector here, forget about this vector for a second, times the sum of the marginals of those elements that you have not picked up yet to the 1 minus phi. And that again, because you have a submodular function that is monotone, you can lower bound by the primal gap between the set Si minus 1 and the value of the optimal solution. So what you again get is that in iteration I, you basically pick up some constant factor here times the primal gap to the 1 minus phi. Whenever you have these types of inequalities, you just solve the recursion and then you obtain your convergence rate, or in this case, the approximation guarantee. So the approximation guarantee and the convergence rate here are actually quite similar. The way of how you should think about it, you let the algorithm run for a certain number of iterations, and the better it converges, the better the solution is in terms of approximation guarantee. Now let me convince you that this actually also works in computations. So my example here is from non-parametric learning on the so-called Parkinson telemonitoring dataset. And the task here is, it doesn't really matter so much what the learning task is. What the submodular function task here is to find an informative subset that maximizes the so-called information gain, which is a submodular function. All right, and so what can you do? So what we did is we actually computed out the true optimal solution. And what you then can see here, this is the performance of the greedy algorithm. So the greedy algorithm gives you basically almost an approximation factor of 1. And then what you have in green, that is my weak or my first attempt at a sharpness notion here. And you see that it does improve a bit, but actually compared to curvature, for example, it's not so great. However, if you use these more advanced notions that are a bit beyond the scope of the talk here today, so for example, this is our best variance, this, the so-called dynamic submodular sharpness, then you see that these notions actually explain a very large fraction of the performance of the greedy algorithm here. So that's about 90%, depending on the budget size. And it's important to keep in mind that the algorithm does not need to know these parameters, but what you do get from the analysis is that the algorithm deforms or performs smoothly as a function of improved data. All right, yeah, so that's just to give you a bit of an idea that this also actually works in computations. And what I would like to spend the remaining 5 minutes on is now my second example from the approximate characteristic theorem. Just to recall, so this is joint work with Surya Combat, my student from Georgia Tech. So just to recall, Carathéodory's theorem here basically states that whenever you have a convex hull of some points in Rn, then every point in that set can be written as a convex combination of at most n+1 points. So what this means, for example, here in 2D is it means that every point inside the set here, so let's say we call this point x star, can be written by at most 3 points as a convex combination. Now, suppose I want even sparser convex combination, and I'm willing to just approximately represent my x star. So maybe I put a ball around that, and I'm happy with any point in that set. And then maybe I can find this point x here, and I can write this point x using only 2 vertices. So that's basically the idea behind the approximate Carathéodory theorem. And for the remainder, the cardinality here of x will denote the minimum number of vertices that you need to write x as a convex combination. Good. So yeah, so what's the problem? The problem is you have a point x star and you want to approximate this point x star with an error of epsilon in the p norm with a point in the convex hull that has low cardinality. And that's the problem. And what do we know? Well, we know that the so-called approximate Carathéodory guarantee that tells us that if you want an epsilon approximation, then we read roughly p times diameter squared over epsilon squared many vertices to do that. And yeah, so first of all, which is actually quite remarkable, but not that surprising if you understand where this comes from, is that this result is independent of the dimension of the space. This bound is also tight. There's instances that show that you cannot do better. And there's various proofs out there. So there's the probabilistic proofs, or actually several probabilistic proofs, but these proofs are typically not implementable because you require an exact convex combination from which you can actually sample, and that convex combination could have a very dense support in terms of the vertices. And if you have an infinite or even exponential number of vertices, you might not want to do that. And then there's a deterministic proof where you basically assume that you can access the feasible region by means of a linear programming oracle, and you solve the problem by mirror descent. So what we are interested in is the question if we can do better than the bounds that you get here, which in some sense, again, are worst case guarantees, if you account for the position of the point x star that you're interested in and the structure of the convex hull that you get from the point zx. So again, our problem data here. And the way of how we want to do that, or what we want to use as a tool, is the Frank-Wolf algorithm. And so you will see in a second why this is an interesting spin to the problem. So what we do is we have our point x star here, and we now write out a convex optimization problem where we have x minus x star 2 norm squared, or p norm squared if you care for the p norm. And what this Frank-Wolf algorithm does is it's basically a first order method to optimize convex function over polytopes or convex sets, compact convex sets. It's a projection-free method because it only forms convex combinations. And what it does is, let's say you have an iterate xt here, you compute the negative gradient, you follow the direction of the negative gradient by optimizing it as a linear function. You get a new vertex vt here. Then you build the line segment and you compute a point on that line segments, either by line search or some step size rule. And you stop when you get close enough to your point x star. Key here is, so you sequentially pick up these vertices. At the final iterate xt, you have picked up at most t plus 1 of those vertices because you do linear optimization, you get a vertex and you form convex combinations here. You can think of this, if you want, as a greedy method for the approximate Carathéodory theorem. And what is important for our purposes here is that you know when to stop. And what I mean by this is that you observe the primal gap because you know what the optimal function value is, which is actually 0 if you actually plug in the point itself. All right, so the reason why you care for using this algorithm is because there's many data-dependent guarantees for this algorithm, and it naturally forms these convex combinations that are helpful here. Yeah, so what do you get? So if you just plug in nothing and you just take the worst case guarantee, you get this PD squared over epsilon squared guarantee. However, if you, for example, assume that your set is strongly convex, then you actually can shave off a square here and you get only, you only need 1 over epsilon many vertices. Similarly, when you assume that x star is in the relative interior of your set, then you can even do much better. You get only a logarithmic dependence on 1 over epsilon. And the trick really here is that you leverage this adaptivity of the conditional gradients of Frank-Wolf algorithm. And there's many of such results out there. In particular, you also get adaptivity for uniformly convex sets that even allow you to interpolate between this 1 over epsilon and 1 over epsilon square between these two cases here. All right, I think that's all that I have for today. Thank you very much for your attention.